Om Bhurbhuvasvaha Tatsaviturvarenyam Bhargo Devasya Dhimahi Dhiyo Yonah Prachodayat.
Okay. Today in this session we'll talk about paging. So far we have seen that there are many memory management techniques, and these are the policies of an operating system when a process comes, when a program is to be loaded into the memory, where this program has to be given place in memory. Okay. This policy is actually dependent on operating system, and operating system has many memory management techniques which allows a program to be placed at any place in the memory. So we saw that there are different memory management techniques. We saw those memory management techniques which allows a process to sit continuously. Okay. So we call them it as contiguous memory allocation strategies. Contiguous memory allocation strategies. The drawback with this memory allocation strategy is, suppose I have a memory, okay, and if I want to load a program into this memory, then comes a process. Suppose if this process has been allocated, has been given some space as memory, okay, and this is the empty space. Assume that here also one process is sitting, and assume here also some process is sitting, and assume that this is empty partition and is also empty partition. Okay. And the size of this partition will be suppose 5 kilobytes, and the size of this partition is 3 kilobytes. Now I want a new process whose size is 7 kilobytes, okay, to be executed. Now in contiguous memory allocation, I cannot do this. Okay. If I want to load this process into the memory, I cannot do this, because this memory allocation strategy supports the process to be the process has to be set continuously in the memory. We have memory which is of 8 kilobytes, but because it is not present continuously, it is not possible. We saw that in dynamic memory partitioning technique, the solution is compaction, but it is very costly. The problem here is our process, okay, which is of 7 kilobytes, unable to execute even though memory which is greater than the size of this process. But this free partitions are not present continuously. So we look for should look for a different strategy which allows us to load a process continuously in the memory. Now, in order to support this, and that kind of strategy, we call it as non-contiguous memory allocation strategy. Non-contiguous memory allocation strategy. And here we saw contiguous memory allocation strategies. Namely, there are multiple partitioning with fixed size MFE, okay, and multiple partitioning with variable number of such as MVT, and dynamic memory allocation technique. Dynamic memory partitioning technique. Okay. Now all of this memory partitioning technique suffers with this problem that they cannot accommodate a process non-continuously. If you want to load a process with any one of this memory allocation strategy, then we need to have continuous memory. In the memory we need to have a continuous partition so that the entire process can sit continuously. Okay. That is the drawback. To overcome that, we have non-contiguous memory allocation strategy, in which if the same situation arises here, it is possible that 5 kilobytes of process can sit here, and remaining 2 kilobytes of process can sit here. Still we have a byte of memory free. Now it is possible with the help of this non-contiguous memory allocation strategy. So what is the technique? What are the examples, okay, which allows our process to be loaded non-continuously in the memory? So one of the techniques, very famous technique, is paging. Okay. So paging is a technique which allows process to sit in the memory non-continuously. Okay. May continuously or may not be continuously. It depends on context of memory and how free frames are available and all. So now let us discuss how this paging works. Working of paging. So first of all, it is a technique which allows a process to sit non-continuously in memory. Okay. Now, how does it works? It works like this. Now, we'll see a simple C program. Suppose if I have a C program, I have written a program p1.c. Okay. Suppose here I have written int main. I have written int a comma b comma c. Make like this, some amount of memory allocated here. Actually, variables which actually signifies the memory location. These are the names of memory locations A, B, and C. Okay. Now, when this program is given to a compiler, a C compiler, what happens? C compiler will give obj file actually. Okay. Now, I have seen software and we have also included stdio.h. Now, this obj file actually contains what it contains, binary code. Okay. It contains actually an exe. The difference between obj file and exe file is, this ABC, for this ABC which are of type integers, they need to be allocated some spaces in memory, but where they will go and sit in memory we don't know. So compiler will generate actually few addresses, okay, which are not actual addresses, so we call it as virtual address or logical address, and assigns them. So here there is some address which is given for A, B, and C, which is not actually real, okay, which are actually generated by the compiler. Okay, they are actually logical addresses. Okay. Now we also called it as, these are called references actually, okay, unresolved references. So when this obj file, now actually when we use printf, scanf, any library functions, the code for printf and scanf is not available. Then where this code of printf and scanf is available? Is it available in #include stdio.h? No, it is not available in header file. In header file, what is available? Only the prototypes of methods, functions are available. Okay. So the actual code will be there in libraries. Okay. Wherever we install, any C, we along with that, software, you'll have a lib folder. So in that lib folder, you'll have all library files. So in order to link those libraries with this obj, we'll use what? Linker. Okay. Linker comes in the picture. Now this linker, it links this obj file along with the library which is there in lib folder. Now, is this libraries are needed to be, this libraries contains the code for printf. Okay. Now, is this printf code is written in C or this is compiled version? Actually, these all libraries will be in .obj. They are actually the compiled version of the codes. Okay. They are linked. Will get p1 dot is also a binary, and here you will have unresolved references. Here you will have resolved references. So these resolved references doesn't signifies that where this instructions will, where this will be allocated space in the memory. We don't know still. And here assume that we have memory. Okay, we have main memory, and main memory can be seen as a sequence of words or a series of bytes. Now it depends upon the type of computer. Earlier, we have only byte addressing, but now we have addressing. Now the size of the word depends upon few computers support 1 byte, few computers supports 1 word is equal to 2 bytes, 1 byte is equal to a word is equal to 4 bytes. Okay. So it depends on in this system 1 word is equal to how many number of bytes. Okay. If it is 2 bytes, then 32 bits will be allocated for addressing. If it is 1, only 8 bits will be for addressing. If it is 4 bytes, 32. If it is 2 bytes, 16 bits will be allocated. Now this is actually exe, which is there in the hard disk. Okay. Now this has to be loaded into the memory so that it becomes a process. Now in order to load this, okay, we need one more entity called loader. Okay. Now this loader will not directly into the memory because loader doesn't know anything about the memory. What is this memory and where can I load this? Where can I load this exe? Okay, the loader doesn't know. It's very innocent. It knows only how to take this p1.exe and put where it has been directed. So what does it do is here the role of operating system comes here. Okay. Now this loader contacts this operating system, and operating system, depending upon its policies, allocation policies, okay, it will allow this process p1.exe file which is there on hard to be loaded into the memory. As and when it gets loaded into the memory, depending upon any one of these operating system policies, okay, now it becomes a process. Now in this entire process, what is happening here? In this entire process, actually we are getting resolved references here, okay, and moreover we are getting resolved references here. Actually, these are the different addresses, okay. We call they are all logical addresses. Now at the time of loading, when it contacts to the operating system, now it is on only operating system that where this p1.exe has to be loaded into the memory, wherein the actual address in the memory will come into the picture. So far, these are all addresses, okay. The addresses which has generated by the compiler are at compile time, we call it as compile time binding. So actually we have got three different kinds of binding. It is an association between this instruction, where does it goes and sits in the memory, okay. The association of instruction, the addresses in the memory. Now here the compiler may say A will go and sit into the address 20, for example, okay. Now this 20 is what? Is it an actual address, is it a logical or virtual address? Okay. It depends. No, actually it doesn't depend. It is actually a logical address, of course. Compilers always gives logical addresses, and these logical addresses are used by the loader, okay. The loader also take this references, take this and give it to the operating system, and it is the operating system which takes this resolved references in p1.exe, and now here actually what happens is you have actually CPU, right? In CPU, if the loader has loaded this process into the memory, okay, those instructions has to be given to CPU or not? Yes, they have to be given to this CPU. Now when these instructions are given to this CPU, now CPU sees what? It sees only logical addresses, okay. Now actually the logical addresses are actually generated at compiler, they are actually generated by the compiler, and at the time of linking it has been resolved, okay. All these references have been resolved, okay. So these are all compile time addresses. Now at the time of loading also, it tells it has to be loaded where it has to be loaded in somewhere 100 in the memory location 100. Now this 100 again is not a logical address, it is not a physical address, this is also a logical address, okay. Now this kind of binding between instruction and the memory address is called load time binding here, okay. Now again this address which is 100, which is resolved, okay, will be given to operating system takes it and gives it to the CPU. So CPU actually these logical addresses, and what does it do? To put buses. These are all buses. Now if it really want to do mapping with this to the physical memory, it cannot do so because these are all logical addresses, okay. They are not really existing, okay. Really existing are physical addresses, okay. Now this logical address has to be converted into physical address. How does it do? Now the CPU has one unit called MU, memory management unit. What it do is memory management unit, okay, is a logical address. Actually logical address who is giving to memory management unit? CPU is giving, okay. We said CPU always generates logical address, okay. Yes, CPU is actually a dummy object here which takes this address and just provides it to MMU, okay. It doesn't generate actually. Actually, who is generating this? Compiler. From compiler it has been resolved and it has been given to MMU. Now MMU, what does it do is it takes this logical and converts it into physical, and these physical addresses will be kept onto the buses, and memory will be accessed, okay. So in this way, here we have three different types of addresses, okay. One type of addresses given at the compile time is called compile time binding, and one address is time is called load time, and one address is given at the time of runtime, which is when we have given it to the CPU converts it logical address to physical address. We call it as runtime binding, okay. So this three type of address bindings are very important. This normally happens. How does a C program execute actually? In this way. Now the problem here is this process was earlier continuously in the memory. Now what do we do is, in paging technique, what do we do is we divide this exe file in number of pages. Actually this is the program, this is a process which we divide into number of pages, okay, and our memory will divide it into number of frames. So paging is a technique in which a process will be divided into pages and frames, and memory will be divided into frames. There is one condition given in textbooks that frame should be equivalent to size. It is not necessary. Take an example of Linux operating system. Linux operating system takes frames of variables. Okay? Not equal to surface. Okay? An exceptional case. But for solving problems are concerned, we actually say that the size of the page should be equal to the size of the frame, or vice versa. Now, what do we do is, just we'll see how this process will be divided into pages, and how this will be divided into frames, and how it's possible to load a process non-continuously using paging techniques. Afterwards, we'll solve problems on it. Now, assume that I have a process P1 and I have a memory, main memory. Okay. Now, this process, what do I do is I will break processes into number of pages. Okay. So I have broken down this page 2, page 3, page 4, page 5, page 6, page 7, page 8 process A. What do I do? What do I do is I'll similarly divide my memory into frames. So assume that I have big memory. This memory. Now here I am showing that there are less and more frames beginning, because we didn't discuss virtual memory concept so far. So this is main memory, and I'll call this as frame 1, frame 2, frame 3, 4, frame 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, for example. Okay. Now, when this process has to be loaded into the memory, how does it gets loaded? Now, there are many possibilities. All these pages P1, P2, P3, P4, P5, P6, P7, P sit continuously in the memory. It is possible, but if it is sitting continuously in the memory, then there will be no difference between memory allocation techniques which are contiguous and non-contiguous, because paging supports non-contiguous allocation of memory for a process. That's why it is possible that this process may sit at different parts of frames in a memory. Now a problem arises. How do I know that? Assume that if this page P1 is sitting here, P2 is sitting here, P3 is sitting here, P4 is here, P5 is here, P6, P7, P8. So all this, the entire process is there in the memory, but it is non-continuously. It is possible that there is another process. Now I can have another process. I will call it as a process B. Okay, it has been divided into page 1, page 2, page 4, page 5, page 6. Okay. So for this, I'll call it as page 1, B, 2, B, 3, B, 4, B, 5, B, 6, B. I'll call it as page 1, A, 2, A, 3, A, 4, A, 5, A, 6, A, 7, A, 8. Right. So I'll put just A, just for our convenience, that this is page which belongs to process A. Okay. Now it is possible that process P1 page B may sit here, process P2, page 2 for process B, page 2 may sit here, okay, P3 B may sit here, P4 B may sit here, P5 B may sit here, P6 B may sit here. Okay. Now see here, there are two processes which are sitting, they are sitting non-continuously in the memory. It is now the problem here is, how do I know that this process is page 1 is sitting in the memory? Now this problem, in order to resolve this problem, we'll have a mapping table called page map table, or we can also call it as page table. Okay. Now this page table gives us information about where this particular page resides in the memory. So actually this page contains fields. Firstly we take only two here. The first field we have page number of this process. This is for process. In every process there will be one associated page B. Now this process A has actually 8 pages. So I'll have 8 pages in my page table. I'll have entries in my page table. Okay. 4, 5, 6, 8. Okay, 8 pages are there now. Now how do I know this page is in which frame number of it? Okay. Now in order to resolve this, okay, I'll have like this. Okay. Page 1 of process A sitting where page 1 of process A sitting in frame number 11. Okay. Similarly, page 2 of process A, page 4 of process A, page 6, page 7 of process A, where they are sitting. Now you can fill along with me this table now. P2 of A is sitting in F5, P3 of A can sit in F1, and P4 of A is sitting in F14, and P5 of A is sitting in F9, P6 of A is sitting in F3, okay. P7 of A is sitting in P7 of A is F12, okay, and P8A is sitting in F15. Okay. Now this is called paged map table or table, whatever you call it. It has page table also. This page table for process A and page table for process B. Now similarly, okay, fill this. Okay, I have this page number and also frame number. So page 1 of B, page 2 of B, page 3 of B, page 4 of B, page 5 of B, page 6 of B. So page 1 of B is sitting in page 2. Now page 2B is sitting in 6. Page 3B is sitting in F10. Page 4B is sitting in F13. Okay, and page 5B is sitting in F16. Page 5B, sorry, page 5B is F16. Page 6B is F7. Okay. Now what happens is whenever a process when you access page 1 of process A, now what happens? It's actually sitting in memory. How CPU will reach this page of A. Now see that it takes only logical and it just logical unit. Now what does this memory does? Address, okay, it logical address done in such a way that it can be set to parts. Okay, one is page number and also page number. So here you'll have a page, and in a page it has lines. It's something like you have a book. Okay, in that book every line is similarly you have a page every line. So the page, okay, the logical address which is given by the CPU will be split into two pieces, logical address and offset page. Now what this memory management unit is, this memory management unit will take, what does it take? It takes logical address. After taking address, okay, it is it's logical address offset of that page. After submitting that, it will have this logical address this page into frame number. Okay, from this number, it gets physically there in page 11. Page frame 11 is here. So in this way, the respective can be accessed. Now here we write that CPU generates logical address space. Okay. So this logical address space has been divided into page number and offset. Okay. Now this page number will be looked into this mapping table. Okay. And when we get this mapping table, we'll get this frame number. Okay. So when we get this frame number, now this frame number, you have a physical address. This is our logical address. Logical address will have page number and offset. Physical address will not have a page number. It has a frame number. Okay, frame number and offset. Because offset is same, because we have one condition here. The size of the page should be equivalent to size of frame. By seeing this condition, offset can be copied as it is. Okay, and the frame number will be taken from this mapping table. Thereby, it gets frame number and offset to actually access a desired page, which is P1 of A. Okay. Now, this is how your logical address has been divided into page number and offset, and physical address is divided into frame number and offset. Now, when we have taken an example where the number of pages in logical address space. What do you mean by logical address space? It is the range of total number of pages that can be accommodated, right? That can be generated is called logical address space. And total number of physical frames which are available in memory, we call it as physical space. Okay. So this page number, we were actually talking about. This page logical address space will be converted into physical address space. Okay, so this here in this example we have less number of pages, more number of frames. Okay, it is for our convenience we are taking, but some virtual memory is different, wherein you will have more number of pages available, because you are allowed to generate any number of pages, but the amount of memory is finite. The amount of memory is limited. Now the problem here is I those big addresses. Okay, into a small address. Okay, we'll use it. So a system, the CPU will generate a logical address space, and the logical address space is far greater than the available physical address space. Okay. Here for our understanding purpose, we have taken physical space to be smaller than the physical address. Okay, the logical address space will be limited. Now, it is also possible that if inside this process, if there are few routines, okay, which are common, then sharing of pages is also helpful, okay. So that every page can be shared in memory, and more than two processes can use them. So sharing of process is also allowed. Now, what are the advantages of paging? We'll see now. There are many advantages of paging. The very first advantage of paging is process can be allowed to sit in the memory non-continuously. Second is, it never suffers from external fragmentation. There will be no external fragmentation. And more sharing is possible. Okay. And moreover, the thing is, all these things, okay, it seems to be how to convert this address into physical address. You need about, okay. CPU will, memory management unit will do on behalf of you, so we need not bother about that. Now, assume the situation, if you don't have MMU CPU, then you have to do a lot of things. It have all those address bindings, where this instructions will be loaded into the memory. All those things, the burden will be more on OS and loader. So that's what the importance of memory management unit here. So memory management unit is actually making your program flexible so that it can be executed in any area of your memory wherever it is available. So there is no question of continuous setting of a process in the memory. So and there is no external fragmentation, and sharing of code is also possible. Moreover, with the help of paging, this entire technique, we need not do MMU can do that. That's why it is transparent from the user. Okay. It is transparent from the user. User need not aware of all these things. Okay? He has just type the program, it will go on. It is operating system and MU on behalf of you. But there are few drawbacks with this approach. The drawback with this approach is drawbacks. The following are the drawbacks here. Let me erase this and discuss the drawbacks here. The first drawback is, yes, of course, it doesn't has external fragmentation, but it suffers from internal fragmentation. But actually, the internal fragmentation of paging is called page breaks. Actually, what do you mean by page break? Assume that I have a process of 7 kilobytes. Okay, now I want to divide this process into pages, okay, and assume that the size of each page is 2 kilobytes, okay. Now, if the size of each page is 2 kilobytes, then I have to cut this process into how many pages? 7. I cannot do it 2.5 pages, okay. 0.5 pages cannot be allocated. So what do? Is we have to sacrifice 1 kilobyte, wherein so that I can divide this process into how many pages? 3 pages, 4 pages. Okay, actually 4 pages. 2 4s are 8. Now here, this page 1 will be completed, it will be filled, and it will also be completed, and page 3 also filled. But when it comes to page fourth page will be 7 kilobytes. The size of 2 kilobytes, 2 plus 6 plus 2, 2 plus 4 plus 2, 6 plus 1 7. 1 kilobyte is free. Now always, page break is nothing but the amount of space which is not utilized within the page called page breaks, and we also refer to as internal fragmentation here. So this is possible, and moreover, in the page only in the last page happens in the page. For a one process, page breaks is not possible in multiple pages. Break for one process is only in one page, and that too, the stage of memory will be less than size of the page. Okay, so it is very here. You have to take again decision. What should be the page size? Okay? Now do the page 2 kilobytes. It is 2 kilobytes, and the size of the process is a number of pages, and all the pages I need to maintain. So that so what is the size of the page? 4 kilobytes, for example. If 4 kilobytes, then what happens? I have less number of page table, but I may get more fragmentation in the last page. So taking decision is now. That's what Linux takes to accommodate these pages, and now let's see a few problems on this paging and see how does actually it works and how to solve these problems on paging. So before we start this paging, I'll discuss a few more points on paging. That we talked about this page table. Now where this page table is actually sitting? Is it sitting in hard disk or in main memory? this page table is also in main memory. Now the problem here is whenever suppose this process, I have a process P1, and when it is read into the memory, okay. Now if I want to access this process P1 directly in one memory access, I could able to access the contents of this process, right? But now with the help of with paging, what happens is the scenario is changed. How? The page 1 might be sitting, page P1 of process A might be sitting here, and page will be sitting here. Now in order to access this P1 of A, some reference to the page table, I'll get address, and using that address, I have to do another reference. So there is one memory reference and there is another reference in order to access one frame. So the performance of paging guides here is, in order to access one frame, I have to do two memory accesses. Okay. Suppose the amount of time taken for accessing a main memory is 100 milliseconds, then accessing a page will take in paging. Okay, it takes double of this time, because one for page table access and another is for actual frame access. Okay. So this is what the sacrifice we have to do, of course, because it has a lot of benefits. Okay, non-contiguous allocation of process possible in paging, and less internal fragmentation, which is limited to less than page size. Now there is another concept called segmentation as well. Now what happens segmentation? Segmentation is very simple. Here what happens is you have a program or a process. This process is divided into segments. Okay, these segments can be this main function, okay, some subroutine, okay, some stack, okay. There are different parts of the program. It has to be divided into different segments. Now I'll call it as segment 0, and I'll call it as segment 1, and I'll call it as segment 2. Okay. So there are actually the process has been divided into segments, and which segment is sitting where in the memory, I don't know. So in order to resolve that, I need to have segment table. Okay. Now suppose the size of this is 100 and the size of this segment is 50 and the size of this segment is 25, for example. Now here I'll have main memory. So where in this main memory this segments are sitting, in order to help this I have a segment table. Now what is this segment table does? This segment table contains segment number and frame number. Segment actually not frame here, because frame doesn't come only in paging. So I'll have a segment number, and I'll have two registers, register and limit register. Base register generally tells me where in memory actually this segment is going to start, and limit will tell me what is the size of this segment. Okay. Now assume that for this base is 100 and this is 20, for example. Sorry, not 20. The size of segment 0 is 100, so it will be 200. And segment 1, okay, if it is starting at for example 100. Okay, then size how much? 50. So ultimately only. Okay. For segment 2, starting at 700, size is 25. Okay. Now here you'll have all memory addresses. These are all words, for example. Okay. 0 to 1 MB, for example. Okay. Now when 0 is in is 0, so base is starting from 100. Suppose 100 starts here. And the length is again 100, so segment 0 will be sitting here. Okay, 50, 100, 200, 300, I'll take it as 400, 500, 600, 700. Okay, the segment 1, okay, 600 and size is only 50. Okay, so 650 will be for this segment. Okay, and segment is starting from 700 and size is only how much? 25, which is equal to 725. So what happens here is logical spread in segment offset with segment. So here it will number and get the proper base and limit register, and it tries to access where actually the segment is sitting, memory. So this is how the access segmentation works. Now there is the problem here is the advantages of segmentation. The advantage of segmentation is we could able to allocate. We could able to divide this process into number of segments. But the problem is it suffers from the advantage is it never suffers from internal fragmentation, but the advantage is it suffers from external fragmentation. Okay, so in the next session, how the segmentation works, and we'll take a discussion further.